Today we're going to talk about using the Intel C++ compiler within the Visual Studio environment. We're going to talk about advanced optimization and test tools. We're also going to look at the OpenMP API for adding threading to an application without a whole lot of effort. And then finally we'll look at the Intel threading tools to take advantage of the multi-threaded processor architecture. We're going to start by looking at the middleware server application. This acts as an intermediary between the clients and the database server. Using middleware servers like this makes it easier to implement business logic without as much of an impact on your client applications themselves. So since all of your clients are going through a single point of contention, essentially, the middleware server, it's important that it's highly optimized and that it's very efficient so that it can scale properly and hopefully with minimal hardware deployment needs. So in the starting point, this middleware server is single-threaded and unoptimized. It listens on a network socket for XML RPC requests, then it takes action to retrieve or update customer data. So we'll need to build the project initially, and then we're going to want to establish a baseline performance level. Without a benchmark, it's almost impossible to really get a good grasp on the effect of different changes you make to the application. You're going to want to know if replacing the compiler really is a good idea, so you'll need to have a clear understanding of existing performance. By taking objective benchmarks, you can identify characteristics such as CPU usage or memory utilization, how much network access is going on, any relevant information for measuring performance, and then as you make changes, you have an objective, measurable way of comparing to see if those changes have really had a net positive effect. So to begin with, we're going to use Visual Studio with nothing but default options enabled, which is a good place to start, so any changes will either be better or worse in comparison to that. So let's start by building the solution. And debugging the application. Now I mentioned that we want to measure this performance objectively, and we can't just do that with a stopwatch. Ideally, we're going to want some kind of tool to perform the testing for us so that any numbers that came out of it are going to be consistent every time they're run. So this client application was developed with that in mind, and it's going to make it easy to repeat the same tests so that we know without question that we've made a positive change each time. We click the call button, it sends a request, and we can see that the server is responding. When we click the load test button, it sends requests on the specified number of threads with a specified number of requests per thread. In this case, we would be sending 25 requests total over 5 threads. So we can see the requests going through the window. And we can see that we're getting an aggregate of 1.26 requests per second. So we now have a baseline to compare against. We're going to change the compiler and see if we can increase the requests per second. So now that we have objective measurements, we can keep these between the test runs. A very useful exercise is to take this performance information and then as you increase your number of users, as you change memory amount, as you make various modifications, you can graph this information over time. By looking at that, you have a very good visual way of determining what are making good changes. So our first change isn't actually going to affect the code directly at all, at least not the source code. Instead, we're simply going to make a change that will affect the final executable code. Because we've installed the Intel C++ compiler, we can replace the compiler in this project with no more than a few clicks. Clicking the Convert to Use Intel C++ Project System option will update the configuration files, actually generate new project files, so that whenever we rebuild the solution, it's only going to use the Intel compiler. The dialog reminds us that if we make this change, we're possibly going to be invalidating intermediate files. So we're going to clean the project just to make sure. This does not have any effect on your source files. And in just a few seconds, you can see that we have a different icon now for our projects, making it very clear that these are Intel C++ projects. Note that we can convert back to the Visual C++ project system as well. That's at either project level. Or, as we did for the conversion itself, we can affect all subprojects by doing it at the solution level. So let's clean the solution and rebuild. So our rebuild has succeeded, and we're now ready to debug the solution again. Notice that when you change the project system, it does change the startup project. And we're ready to send another objective test using the same client program, which will assure that we have consistent results. Once again, it's verified to be working properly. And you can see that we went from 1.26 to 1.39 requests per second. It's definitely an improvement. Any increase in performance whatsoever is always going to be a gain. And by using a tool like this, we were able to objectively measure it, especially when a small change may not necessarily, a 10% increase may not necessarily be a very large jump. But over many requests, it's very important to get as much performance as we can out of something like a middleware server that's going to be servicing so many different clients. That performance will add up very quickly. In the next exercise, we'll see how to enable advanced optimization techniques by using the Intel C++ compiler's optimization options. So there are different types of optimizations. An optimization can just be what you do to your own code to make things more efficient. But a good compiler also optimizes code by looking at more efficient ways of achieving that conversion from source code to binary code. It can do that by eliminating redundant steps, reordering steps, optimizing memory and cache usage, and all sorts of other things that behind the scenes will serve to increase your performance even though they may be a little bit opaque on the surface. Optimizing at the source code level requires a lot of skill and attention, and sometimes it can impact the readability and maintainability of your code, so it's definitely with some caution that you should approach making changes to the source code. But by making compiler-based optimizations, you don't sacrifice anything in your readability or maintainability, and you still leave it open to further optimization down the road. So let's take a look at how optimizations are configured. Under Configuration, the C++ section includes a number of different categories. Optimization is the most relevant for what we're looking at right now. So we're going to specify maximize speed plus some high-level optimizations. This is specific to the Intel C++ compiler. We'll enable some of the other optimizations, and they will affect the balance between inline code and function calls, optimizations for specific processors, parallelization, other things in order to wring more performance out of the code at compile time. And having specified some optimizations, we'll need to repeat this for the other project. It may seem like it's just extra steps, but In actuality, being able to set different optimization settings for each project gives us a great degree of control. This could be expanded even further with a lot of different sub-projects which perhaps might each have its own reasons for different optimization strategies. And we're ready to debug the code again, which will automatically trigger a rebuild. So we're ready to run the test again. We verified that it is functioning. And you can see we've got our performance to gain again. Once again, the percentage increase isn't necessarily as important as seeing any increase at all. In any kind of high volume application, even the slightest increase is going to add up considerably over a large number of transactions. It's also important to realize that some optimizations are just going to be more effective than others. You might spend a lot of time on a given project just trying different combinations of options, looking at the way your code is composed. Some optimizations are simply better suited for applications with many small functions, many large functions, applications that make more or less use of memory. Depending on the profile of your specific application, your optimization strategy could well change. And it's for that reason that profile-guided optimization is an important optimization to be aware of. Profile-guided optimization is actually a three-step process, and it works by initially compiling your code with a certain flag that instructs the compiler to introduce profiling into your application. The exe that it produces from that then gets executed and used normally. This is the second stage, simply running the application. And while it does this, those profiling extensions that were embedded into the code in the first step are used to generate files that build up a profile of how the application runs. As I alluded to before, some of those things such as memory usage and how certain functions are called actually get tracked and saved out to files, so that in the third stage, the application can be recompiled, but using that information to hopefully develop a better strategy. So we need to go back into the configuration options. And this time we want to specifically add a command line option. And what we want to do is generate profile information, so we'll use the profgen option. And we'll also need to specify that in the other project. And now we'll debug the application, again causing it to rebuild. Now we're going to use the same client program in order to send the requests. And this is important so that we can build up that profile of how the application runs. Any numbers that it generates are going to be fairly useless though, because of the overhead introduced by generating the profile application. The number of requests per second isn't going to be meaningful in this case because of the overhead generated by the profiling. In fact, we could end up seeing timeouts in this situation simply because of how much it's slowed down. And having run this, we've actually generated some extra files. And the compiler will use those files when we recompile the application, assuming that we change the command line options. The profgen tells it to generate those files, while profuse tells it to take those files and to feed those back into the compilation cycle. And it does it this way. This actually allows you to specify that profgen create the exe that way, and you could run the application for an extended period of time, or run it multiple times, and all of those results will be merged together then for the final compilation. The qprofdir option simply tells it where to find those files, so that it knows where to locate the intermediate files. Once again, we'll need to copy those to the other project. and we simply execute it again, which will, because of the change to the options, trigger another rebuild, and this time take that information into account, which will generally lead to an increased compilation time. I will shorten compilation times for the use of the video just so that you're not sitting there watching all of the messages go by. And we're prepared to run it again. And as you can see, ignoring the 1.15 per second line, which was while we were profiling the application, we're now to our highest level yet. So PGO is intended to optimize code based on actual runtime information, so it should always make a really big difference. Of course, with every other type of optimization, it's still possible you may not see the best results here. So using PGO, you get a much more realistic picture of the way the application actually runs, and this should yield better code. But just as with any other type of optimization, it's still not a silver bullet. You still want to objectively measure the code and make sure that you're taking the best steps for your application to achieve its best performance. So changing optimizer settings is definitely a great way to gain performance, but as mentioned, it's not a silver bullet, and it doesn't preclude you from making changes to the source code where needed. By rewriting or by rearranging your code, you can make your intent more clear and you can reduce unnecessary overhead. The optimizer can't make some of these changes. So complementing the Intel C++ compiler is the Intel vTune Performance Analyzer. And this is a great tool. You can determine where your code is spending time, you can identify potential and actual bottlenecks, and it will make recommendations for improving your code. Unlike the compiler changes, vTune isn't actually going to make any changes to your code. It's simply going to call out things that will probably require attention by you. But knowing where these opportunities are can make it easy to create a roadmap for the enhancements that you need to make. A vTune can be launched in one of two ways. There's a shortcut right on the desktop, but it also integrates cleanly with Visual Studio through the tuning browser pane. These two nodes in the tuning browser represent our two projects. We're going to link to the Day 2 server project and create a new activity. Now, an activity is a configuration of what analysis should be run on your code. As you can see, there's a number of types of projects you can run. We're actually going to use the call graph wizard today. And as you can see on the side, this will instrument and profile your application and display a call graph showing critical functions and call sequences. But you can perform various activities here. And so when you select one of these, it saves it as an activity node for your current project. And you could create several of these instances, and then they would be different types of tests that you could run, and then as you made changes, you could rerun a certain activity and be assured once again that you've got objective information you're looking at. That's repeatable. That's not influenced by any bias. So let's go with the call graph wizard. This is Windows profiling. If you're doing a .NET application or a Java application, you'd want to select the right one. This ensures that it's not just profiling the underlying DLLs, but the code that's in your application, so it can get that extra step and drill into your objects in your code. You'll need to tell it what application it's going to be profiling. This is where we will navigate to the exe, and that's how it will know where to extract the information as it's running. And this is what we built in our project. You can pass command line arguments. You can set a working directory, which simply defaults to the executables directory if nothing else is selected. The modified default configuration when done with wizard option enables you to make some pretty in-depth changes if you want to include or exclude additional modules or make other specific changes that are based on your application. In this case, the server exe itself is the only module that we're looking at. And we're ready to profile the application. Now, as with PGO, this is going to introduce some overhead. This will actually be some considerable overhead. We could end up seeing timeout errors in the client, but we don't need to worry about that. As long as the client is sending its requests, we know that the server is being exercised, and we know that it's generating good information for us to review. And the server application is beginning to start up. We'll know it's completed when the dialog pops up and the console window itself says that it's ready to accept connections. So we're ready to send our objective test edit. And now we'll send a load test. So as you can see, the performance information is a lot lower this time, but it's also not useful information. We're not going to use this as any kind of comparison. But we know that we have profiled the information, and we can take a look at it now and see what recommendations vTune might have for us. Now, the profiling information needs to be analyzed by vTune itself before it can show anything. The call graph view helps us to identify critical functions in call sequence. It can show the creation and destruction of threads. It can show what functions are being executed in a parent-child relationship. We can really dig into the results at various levels to see what's affecting what. The top pane breaks down execution from module to thread to function. We can see information such as how many calls were made, how much time was spent in the method, how much time was spent calling out, how much time was spent waiting, where the module itself is. There's a wealth of information here. We can expand and collapse the information in various useful ways. And it makes it very easy to locate specifically what we're interested in. What we want to do is sort the information based on self-time. And self-time tells us how much time is spent by the method itself, not by what it's calling out to. And we can sort it in either direction, making it easy to see from the top to bottom where time is being spent. Thread 0 is the main thread of the application, and then we can see the functions, the class, the number of calls that were made to the function, self-time. Let's take a look and see specifically what self-time is. We can do this with any column through the What's This Column menu command. And this gives us a concise explanation of what the column is used for. So if you're using vTune for the first time, it makes it really easy to get a great idea of what everything is doing. Gets you up to speed in no time. So if we look at what was actually executed, you can see that the work method is at the top of the list. The execute method is the second in the list. These are the places we'd want to start looking in the code to see, is there a way we can optimize it? If we look down below, we can double click an entry here, sync it up, and it shows us exactly where in the stack of calls that this method exists. Instead of in the visual format, we can view it as a call list so that we can see what calls what and what the relative contributions are. In this case, we might want to look at the handle event function, which contributes about half of the time to the work function. In addition to the call graph wizard, we can also use the counter monitor wizard, and this will allow us to capture the values from system performance counters alongside of the profiling of our application. And this is the counter monitor wizard, which, as you can see from the side, it monitors the operating system performance counters and the display counter values over a period of time. So this enables you to see what your application is doing in relation to what the system is doing. Once again, we'll want to specify the server application and automatically generate tuning advice. This is a typical application where memory, processor, and resource utilization needs to be measured. Though it does perform network operations, everything is on the local host in this machine configuration. It's not graphics intensive, and though it connects to a database, it's not primarily a database application. So though we could possibly use network or database, we'll just go with typical utilization to simplify things. We want it to run for as long as the application runs until it terminates, rather than automatically cutting off the application after a preset amount of time. And we're ready to execute. Once again, we'll execute the client program for objectivity. And of course, we're not comparing measurements anymore. This is going to stand on its own as a brand new measurement. The information is only useful as to what's executing within the application, not the timings that we get. So let's exit the server application. And we'll maximize our space by closing the output pane. And we've got two different panes here. We've got the Intel Tuning Assistant and the Counter Monitor runtime results. The runtime results allow us to see the various counters that we've been collecting. They're listed down in the legend. And then the symbol, and this looks very much, if you're used to Performance Monitor in Windows, this is essentially what you're seeing right here, but with the addition of the fact that it was analyzing the application at the same time. So the Tuning Assistant then tells us two different things that we could use in our own feedback for the application. There are more threads ready to run than there are processors on which to run them. In a heavily multi-threaded application, which this isn't at this point, it's always important to try to have a higher number of cores or processors on your system in order to be able to simultaneously run your threads. This gives advice based on that, and notice that all of them are linked. So this tells us this is extremely relevant for this application. The system's processor queue length is long, indicating that there are more threads ready to run than there are processors on which to run them. At this point, we only have the main thread executing requests and an additional UI thread. So this is something that we would want to review as we add threading more pervasively into the application. Processor utilization is low. You might be accustomed to thinking of this as a good thing. You want your CPU to remain low. You don't want to saturate the system. You don't want to be CPU bound. But this does indicate that we could be doing more with the application. We could be performing more work, getting more done on the same system. So currently we're running much less efficiently than we could be. So by following the results, by clicking on the links to read more information, you can get a really good idea of some changes that you can consider making to your application, along with objective numbers to look at so that you can compare before and after. Threading your applications properly can make a huge difference, especially when you're servicing a large number of users as a middleware application typically would. Being able to service a large number of users is going to hinge on being able to share your data properly between connections, locking and releasing data, and avoiding various errors. The Intel vTune Analyzer can analyze threading errors just as it can other performance errors. So similar to other activities, we want to create a new activity for threading. The category list will change from analyzer projects to threading wizards. And start with the Intel Thread Checker wizard. This will collect data for an executable and then show where there are potential errors. Notice the now familiar look to the wizard, having to select the executable, specify if you want the activity to run right away. We don't need to make any changes, we can immediately start. So the thread checker is going to run, and while the application is starting up and while it's executing, the real-time status will actually tell us when there's diagnostics ready before we finish. It's telling us there's one new diagnostic ready, and we haven't even started sending tests yet. So this is a very powerful feature that enables us to see information very quickly. If we click this button, it's going to update the main window to show us the relevant status information, so we can already see two examples of some possible changes we could make. So let's send a test to it. And we may very well receive timeouts. They're not necessarily relevant as long as we're sending the requests, then we know that we'll be generating some useful information. I've abbreviated the analysis for the sake of brevity. So we have another diagnostic ready. We can exit the server application and we'll analyze the results. As you can see, we're up to 5 possibilities here, 5 messages. It provides us a short description that defines what type of situation it's discovered, the severity, which is coded as remarks or info, caution, warnings, errors, and then a description. And notice this goes right down to the module to tell us where the error occurred. If we're unclear as to what one of these means, we can right-click it and go to Diagnostic Help, or if we're simply unclear about what the column is, we can go to Column Help. Diagnostic Help will tell us specifically what that message means in more detail, including cause and possible solutions. For a closer look, we can double-click one of these lines, and it shows us the 2 threads that are involved when there are 2 threads involved. And we can see specifically what was being accessed at the time. And then it will also show us stack traces. So in the event that you have threads that are colliding with each other, if you have a common variable that's being overwritten by 2 different places, this will detect that, and it will even allow you to see specifically where the 2 threads were at the time and how it occurred. So here we can see that in server.cpp on line 561 and server.cpp in line 589, we had 2 different threads, and we caused a conflict because the memory read in one line conflicted with the memory write at the other line. So this is a situation where it's indicating we could probably use some synchronization to ensure that what one thread is doing to a variable doesn't affect another thread. But at this point, our application is not very multi-threaded. Ideally, we should be spawning additional threads as additional requests come through. Adding threading can be fairly complicated though, so we're going to use the OpenMP directives as a way to easily add multi-threading to our existing code. And OpenMP is very important because it allows us to maintain the sequential flow of the actual code even while we're modifying the way it's going to perform at runtime. It's the work function that performs the work in the application, looping through, finding requests, and dispatching them. The process events for loop is a great place to add a parallel construct. The OMP pragma for OpenMP And then parallel tells it that we would like to create a parallel section of the following for loop so that each iteration of this loop can be run in its own independent thread. We want to be sure that we've locked the section so that multiple threads don't perform the same code, which modifies shared values at the same time. And so the critical block is a construct that ensures that this block of code is locked among multiple threads. Finally, though we don't have multiple cores on this machine, we're going to introduce an OpenMP API call to specifically set the number of threads. We can use other API calls to find out how many threads OpenMP has allocated for its thread pool, and to perform other optimizations that are otherwise performed using various defaults by the OpenMP pragmas. When threads are not CPU bound, it makes sense to have a higher number of threads to ensure that as the data becomes available, there's always code to be executed. The final step is to enable the OpenMP extensions. And we're ready to build a solution. The Intel Thread Profiler will help us to visualize an application's critical path. We can see how to use threading more efficiently, we can identify blocking time, find synchronization issues, and make sure that our thread's workload is balanced. So again, we'll create a new activity. This time we'll select Thread Profiler. We use the same exe, and we're ready to start it. Once again, we may see timeout errors, but what's more important is that we exercise the application so that we have information to analyze. So as expected, performance isn't very high, but we should see now some information related to threading in the application. So we'll exit the server process and allow it to compile the data. And this provides some information that there is contended synchronization detected. And this states that we already have some problems in the code that could limit scalability on more parallel hardware, and this will impact the statistics collected. So it's important to review this information as it analyzes the code so that you can very quickly put it to work and start optimizing to get the best performance possible, especially in threading. By paying proper attention to threading, it makes the difference between an application that will scale well with more cores versus one that simply needs a faster and faster processor to achieve better performance. The timeline view helps you to understand thread activity. You can see why threads are inactive and whether they are on the critical path at that time or not. The above pane shows achieved concurrency levels, in other words, the number of threads running or scheduled to run, as opposed to blocking or sleeping. CL1 indicates relative amount of time that concurrency level is equal to 1. Notice that the highest numbers are for CL0 and 1. With only one physical processor, this makes sense. A higher number of concurrency level than processors is acceptable, but 1 is preferred. Remember that we explicitly specified 5 threads using the OpenMP API call in the main method. Not all threads are always ready to run, though, due to waiting on network reads. By double-clicking on a CL bar, we can view which threads were active during the various levels, and see how much active time, spin time, and wait time they spent. You can also see certain specific activities performed, such as time spent in critical sections or blocked, as well as which system or user module contain the executing code. The Intel Threading Profile and Intel Thread Checker will help you to achieve the best performance possible for your threaded applications running on multiple core or multiple processor systems. Use them as tools when you're adding threading to existing applications and make your code as efficient as possible.